In this video, we have a little bit more on mathematical induction. So let me go over this thing again. Mathematical induction is a method for proving that statements involving natural numbers are true for all natural numbers, 1, 2, 3, and so on. And then the principle of mathematics induction states this. Suppose that the following two conditions are satisfied with regard to a statement about natural numbers. So condition 1, the statement is true for n equal 1. So they'll give you a statement regarding natural numbers. The last one we did, I believe, was the sum of the first n natural numbers was given by the formula n over 2 multiplied by n plus 1. This one is kind of similar. Statement 2, if the statement is true for some natural number k, it is also true for the next natural number, k plus 1. So the situation here is you assume statement is true for n equal k, and then you have to show that it's also true for n equal k plus 1. If you do that, then you've proved the statement, or the theorem, whatever you want to call it. So you can show those two conditions, and the statement will be true for all natural numbers. So here's one problem then. It says use mathematical induction to prove that the sum of the first n even numbers, of course we're talking about natural numbers, even natural numbers, is given by this formula. So the first thing you want to do is show that the formula, the statement, is true for n equal 1. So put a 1 there where the n is. You get 2 times 1 is 2. Now on the right side is the same thing, 1 and a 1. So 1 and a 1 is 2. 2 times 1 is 2. You could do it for the first 3, but all you need is show that it's true for n equal 1. Notice if I put n equal to 3, this is going to be 6 here. Just this one right here. And if we add those up, we get 12. Put a 3 here. 3 and 1 is 4 times 3 is 12. So for the first up to 2, 4, and 6, we can show it's true. But all we need is 1. Show the statement is true for n equal 1. So just plug it in. Put a 1 there, 2. On the right side, put the 1 where the n is. We have 1. 1 and 1 is 2. 2 times 1 is 2. It checks. So condition 1 is confirmed. You can do others, but all the theorem requires is you test n equal 1. And then the next one's the one that's more involved. Assume statement is true for n equal k, and show that it is also true for n equal k plus 1. So here's the assumption. We assume it's true for k. And all I did here is instead of an n, I put a k. Particular natural number. So 2 plus 4 plus 6 plus 6 plus 2 times k will give me k times k plus 1. So all I have to do, if I add the next natural number, be k plus 1, then wherever I have a k, I have to come up with a k plus 1. K plus 1. If I assume it for k, I have k where the n is. In the formula, I put k. So here it is. This is assumed to be true. N equal k. So here I have it, 2 plus 4 plus 6 plus ... plus 2k. And then the next one would be k plus 1, so it's 2 times k plus 1. Now for this part right here, that's the assumption. So on the right side, the sequence there in red represents this. And then I added the next one, k plus 1, so it's k plus 1 times 2, and I get this part. Now I have to show, to complete the proof, where I have, see, and this is a k, but the actual formula, remember, had an n. So I have the k, I have to have k plus 1. Well, this one is pretty straightforward, because you got a k plus 1 here, and a k plus 1 there. So I factor out the k plus 1. And what's left if I take out the k plus 1? Well, I have k plus 2. But let's write it this way so it becomes obvious. K plus 2, that's what we have left. We factor out the k plus 1. It's the same thing as k plus 1 plus 1. So we showed the statement was true for n equal 1, we assume that it's true for k, that's this right here. And if you do that, if you can show it's true for k plus 1, then you've proven the theorem. And this is the final result right here. Where I have the n or the k in this case, you got k plus 1. We got k plus 1, k plus 1, plus 1 here. So we can conclude the statement is true for all natural numbers, and the theorem or statement is proved. Thanks for watching. We'll see you next time.